All right, good morning, everyone. Let's go ahead and get started today. Hopefully I'll be able to get through today's lecture. I'm a little under the weather, but we'll see what we can do. Um, the first thing that if you've gotten online, you've probably noticed is that I have an exam posted. So I'll go over that here in a little bit. Um, Basically, it's just going to be one question, but I have several different options, so each of you will probably get a different question. And what I want you to do is just to go in and paste your code into the box that I provided, and I'll grade it that way. But I will talk about that a little later in the class. What I would like to do this morning, though, is just to jump right in because there's some material that we need to cover so that you're going to know how to do the exam. We've probably covered enough material where you could figure it out on your own if you had to, but I'd like to give you a little bit of insights if possible. So let's go ahead and open up an Excel spreadsheet. Go ahead and open up one of those, and we're going to write a couple programs together this morning. And these should provide some insight for you guys to help on the exam. So let's go ahead and go under Developer and View Code, and then we'll right mouse click and go to Insert a Module. And we'll just start writing. So the first thing that I want to cover this morning, let's just go ahead and type in sub power x colon like this. And I'll explain what we're going to do is what we're going to do this morning is we're going to write a program that basically allows you to take a number x and raise it to the n power. Okay? So let's suppose x is equal to 2 and n is equal to 3. This is just going to be 2 raised to the third power. It's going to be 2 times 2 times 2 is equal to 8. Okay? So you may look at this and say, well, why not just take, x caret n and code and do it that way? And the answer is, well, yeah, that's one way to do it. But this syntax right here is actually exploiting some code that says to take x and multiply it times itself n times. So, part of this program, I want to teach you guys how to do some things that are useful, and we'll get into that more into the course once we go over the fundamentals. And we're at the point now where we're almost what I would consider to the point of learning the fundamentals of Visual Basic. From here on out, it's kind of icing on the cake and being able to exploit functions and features that hopefully are useful. But someone had to tell the computer how to do this. And so what I want you guys to get when you come out of this class, one of the things I want you to get is an appreciation for how computers work and what they really do. So a few weeks ago, I think I gave some insights when I told you that computers can really only do about 3 things. And the 3 things that they can do is, 1, they can add 2 bits together. Okay, so you hear about bits and bytes. Well, a bit in computer science, electrical engineering, is the most fundamental piece of information you can have. So it's just a 0 or a 1. Okay, so you always hear about zeros and ones. And so, the analogy that when I teach fundamentals of computers and these trainers that you see in here, we do a lot with that in that particular course. The analogy that I use with computers is that imagine that, you're on a boat out in the ocean and someone is on shore and you can barely see the boat, and it's night, dust time, and you don't have any radios or anything. How can you communicate? Well, if you have a flashlight, you can turn that flashlight on and off, and that's maybe use something like Morse code. But you've basically been reduced to the fundamentals at this point of, you either see a light or you don't see a light. So it's just like when I walk in the room this morning and I turn the switches on, we could have a code to where, if I turn the switch off, everyone sits down. If I turn the switch on, everyone stands up. Or we could put that on a timer, and every second you check to see the status of the lights. So, like a metronome, is that what it is? And when you learn how to play the piano that goes back and forth, it's like a beat in music. So every second you check to see if the light is on or off. And so we could start developing more complex codes at that point. So like if you see three ons in a row, it means something. If you see, two ons and an off, that can mean something. And we could establish our own code. And in some ways, that's what's happened with computers, is for numbers, you can actually turn these zeros into ones into real numbers, and it's a direct one-to-one conversion. For like representation of letters or characters or symbols, it's somewhat arbitrary. We just simply say that a series of 11001111 represents maybe an A or B or Z or something like that, and we've just accepted this as a human race in regards to computer science, just like we have certain languages. So they can add two bits together. They can count. So the way they count is they literally just do something like they start at, say, 0, 0, and then it'll go to 0, 1, and then 1, 0, and then 1, 1, and then it'll go 1, 0, 0, 1, 0, 1, and it can count. And you may say, well, how do you know that it counts like this? Well, all I'm really doing is I'm just counting in base 2, which is, we're used to base 10 fingers, but you can have any numbering system you want. You can have a base 11, you can have a base 13, you can have a base 4, a base 60. That's what I think the ancient Sumerians had, and that's where 60, minutes, 60 seconds, 360 degrees in a circle came from. So, instead of having like 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, they had 60. So this is pretty easy to do, and they can compare two bits together. Okay, and that's pretty much the only three things that computers can really do. You can say, well, they can reference memory and they can do all these things, but fundamentally, this is about it. There may be another thing or two that I've kind of forgotten or, not really taken into account, but for the most part, this is all computers can do. So from these three things, we can do all the mathematics and all of the number crunching and all of the animations and everything that our computers do based on these three things. And these three things are done with just this little transistor that's essentially nothing more than an electronic switch. So if you ever hear about a transistor, that's all a transistor is. Just imagine that switch over there being on or off, but instead of two wires coming in, you've got a third wire, and that third wire is just your finger. So if you send that transistor a pulse, it'll turn that transistor on. If you don't, it'll be off, or you can do it kind of back in reverse. So that's all a transistor is. It's literally just a light switch with a third wire coming in, but instead of it being mechanical, to where you're actually, click, click, click with your finger, you're able to send it a pulse, and that pulse, or that voltage that you send it, actually activates or deactivates that transistor. Well, then you can start imagining, well, what if I hook up other transistors to activate other transistors? And it's like, well, welcome to the modern microprocessor. So we're not going to get on this level, okay? We're not going to reduce it down. That's for another course. But what I want you to have in this assignment that I'm giving you is an appreciation for what the computer is doing based on fundamental operations. So we're going to figure out how to calculate sine, cosines, and tangents. Basically, all you're going to be able to do is to add numbers and multiply numbers. You can say, well, it looks like you have to subtract and divide. Well, subtraction is just the opposite of addition, and division is the opposite of multiplication. Um, and I'm going to show you how to calculate, some complex functions. Okay. So the first thing I want to do this morning is let's go ahead and open up this code, and we're going to write a really simple program that raises one number to a power. Okay. So the first thing we're going to do is we're just going to type in x is equal to input box, and I'm just going to say input x. Okay. So this is just getting the value of x. Then I'm going to say n is equal to input box. I'm going to say input n. So all we've done here is just figured out a way to get the value of x and n. You could actually hard code them in, but then you couldn't change them, or you could link them to a cell. But this is just one of the easiest ways. And then I'm going to write a little program, a little for next loop. It's just going to say for I equal 1 to n. I'm going to say, oh, I'm sorry, right here, let's type in power is equal to 1. Okay. I'm going to type power here now is equal to power times x. And then I'm going to say next I, and then MSG DOX power. And that's it. That's all you have to do to raise something from a number to a power. So let's think about how it works. Let's suppose we put in a value of x is 2, input box n is 3. So power is initialized as a variable being equal to 1. So then I say for I equal 1 to 3. So power is equal to power, which is 1, times x. What is x? X is 2. So power is now equal to 2. Next I. I is equal to 2 now. So power is equal to power times x. Power is equal to 2. X is equal to 2. 2 times 2 is 4. Next I, because we said n is equal to 3. I is equal now to 3. Power is equal to power times x. Power is equal to 4. 4 times 2 is 8. Next I is equal to 3. So this loop drops out because we've reached 3. And then we just do MSG display whatever it is. So if I hit run here, I say input x, I put input 3, I get 8. So, let's try a number like 2.5 times, let's see, go clear. Let's say we have, let's say 2.5 to the third power, okay? So if I run this, I go 2.5, plug in 3, we get this, okay? Now, in this particular case, n has to be an integer because we're doing a for next loop. We're going to learn how to do this problem without them being integers. But for the time being, I think it's kind of obvious why n has to be an integer because this is a for next loop. Okay, so we're counting from one number to another. So if I go for I equal 1 to like 2.5, what happens is it drops out at 2. Because as soon as it hits 2 and then goes to 3, it says, oh, 3 is greater than 2.5, so I stop at 2. So for this particular problem, n has to be an integer, right? Pretty simple. So everyone has an appreciation now for how you take a number and raise it to a number, another power, okay? All right, let's go through now and let's insert another module. And let's call this one, let's say subfactorial, like this. So is anyone in here, or is everyone in here familiar with the factorial function? So if you see something like 4 factorial, do you know how to calculate that? Did you ever come across that at any point? All this exclamation point is, you're going to get it immediately. It's just 4 times 3 times 2 times 1. That's it. That's all a factorial function is. So if you see 6 factorial, it's just equal to 6 times 5 times 4 times 3 times 2 times 1. Turns out this is a very important function which you'll come across in different classes that you take. So how hard is it to write a program to do this? Well, actually, it's not much more difficult than the one we just wrote. We're going to say n is equal to input box, input n, like this. And I'm going to say fact is equal to 1, just to start out with something. I'm going to say for I equal 1 to n. Come down here and type in next I. Go ahead and get that. And I'm going to say fact is equal to fact times I. And I'm going to say MSG box fact. So the only difference in this program and the last program, if you look, is before I multiplied power times x, which was the original base, and I just kept multiplying it times that base. In this program, think of it as the base is changing. So let's go through and run this. And I'm going to put in something like 4. So what we get? We get 24. Well, does that sound right? 4 times 3 is 12, times 2, 12 times 2 is 24, 24 times 1 is 24. So yeah, that appears to be right. So let's go through and see how this thing actually works. So looking to see if there's I know there is. And I'm going to go into step into, yeah, because if I hit F8, there's a hotkey on my recording software that tries to stop. So what you can do is hit F8, or you can click on this button that I put on, and it's called step into, so it allows you to debug or run your program a line at a time. So I'm going to step into it and see how it goes down one line at a time. So I step again. It says, all right, input value, so I'm going to put like 5. It comes back here. And it allows me to hold my cursor over and see what's actually going on. So fact is equal to empty yet because I haven't yet run this line, so I'm going to step. So now fact is equal to 1. So now for I is empty because I haven't run this line yet. For I is equal to 1. So this is going to be fact is equal to fact times 1. So 1 times 1 is 1. Next I. So now I is equal to 2. Fact is equal to fact times 2. 1 times 2. So now fact is equal to 2. Loop again. Fact is now equal to 6 because this value was equal to 2. This value is equal to 3. So fact now is equal to 6. So then I'll multiply fact again times 4. So now fact is equal to 24. I is equal to 4, but we said for I equal 1 to n. N we said was equal to 5. Let's run it again. So now fact is equal to 24 times 5, which is 120. Fact is equal to 5. Now this will drop out of this loop, and it gives me an answer of 120. Okay? So, everyone got that? Pretty simple. Okay? So you may look at this and say, well, I mean, this is kind of boring. It's like, yeah, it's kind of boring, I guess, until you have to do something with it, and it's not so boring. So what I want to show you with these two simple programs is we just took two functions that are two of the most commonly used functions in higher mathematics, and we just wrote a simple for next loop to give us the answer. Okay? So, you know, one of the things that I don't think in modern times we have an appreciation for are calculators. But trust me, if you had to go back before there were calculators, you would have a huge appreciation for calculators. And, you know, it used to be long division, long multiplication, all that sort of thing. And then they come up with logarithms and how they work, and I'll talk a little bit about that. But there was an extremely useful function for logarithms back in the days of just doing general mathematics. If you had to multiply or divide two very large numbers together, you use logs, and it allowed for a shortcut. Okay. So, are there any questions on how we wrote those programs? Pretty simple. Now, could you have figured it out on your own? I don't know. Maybe you could have, depending on your level of skill with Visual Basic and programming. But I still am a big believer and a big fan of the way you learn, instead of me giving you a problem and you just trying to slug through it, is let me show you how to do a few. And that becomes kind of, oh, I see what you're doing with this. So this is a really, really, really simple program if you think about it. There's not much to it. So now what we want to do is we want to expand this a little bit. And I want to ask a question like, well, let's suppose that we have a number like e to the, I don't know, third power. How do we solve that? Well, does everyone know what e is? It's the natural log. Everyone familiar with that? Is there anyone that's not? If you are, don't feel bad about it. Okay. E is this number. It's kind of like pi. Pi is equal to 3.14159. E is equal to like 2.7182818 and something else. Okay. So it's a strange number, just like pi. So why does E exist? Well, E, it crops up in all of science and engineering. It is this number that kind of reveals itself at so many levels. So one of the most famous examples of E, say e to the x, is if you take the derivative. Let's suppose that you have f of x is equal to e to the x, which is just a function, and you take the first derivative of this, it's e to the x, and you say, well, wait a minute, what's the first derivative? Well, it's calculus, okay? But what happens is the derivative of the function is itself, okay? Or if you integrate it, which is kind of calculus too, you integrate the function, it's itself, and it's the only function that's like that. So any other function that you integrate or take the derivative of, it's not itself, it's something else. So essentially what this means, if you were to plot e to the x, it looks something like this. And you were to ask the question, what is the slope at any given point? The slope, how steep it is at that point, is the same value as the height above the ground. Okay? So the higher you go, the steeper this gets. So the higher up the mountain you go, the steeper it gets. But that slope, how steep it is exactly equal to, say, the elevation that you set at. And so that's kind of unique. That's just kind of interesting. So this number is used all of the time. I just can't express how much e is used. The natural log of x is essentially the opposite of e. So e in natural log is kind of like addition and subtraction. They're inverses, multiplication and divisions. So if you say, well, what's the opposite of e to the x? The opposite of that is the natural log of x. It's the inverse. Okay? So don't worry too much about it if you don't really know what it is. What we're going to do is we're going to write a little program that calculates e to the x. Or I could just come in and say, we're going to write a program that calculates 2.7182818 raised to the x power. So you could we could just rewrite it like this. You say, well, where'd this come from? Well, this is e, and it comes from something that you're going to learn later on. So how would we go about doing this? Well, we're going to use something that's called a Taylor series expansion that you'll learn about probably in Calculus 2 if you take the course. And it's essentially an approximation function. So, I've provided a link that talks about Taylor series expansions. And one of the expansions that we're going to look at is this guy right here. So basically, years ago, somebody really smart figured out that if you need e to the x, right, what you can do is plug into this formula, which is essentially this formula right here. Now notice what we have here. We have two things. We have an x to the n, which is x raised to the first, second, third, fourth, and so on. And we have n factorial. Okay? So the reason why I just wrote those little programs with you to raise something to a power, an integer power, and to take the factorial of something is because those are two functions that are needed to calculate e to the x, all right? Which is one of the most useful functions in all of mathematics. So what I want you to think about, though, just for a moment, is how we can turn these functions into just simple either adding or multiplying and counting. So when you look at the functions that we just wrote, just look at it just for a moment. All this is counting, right? For I equal 1, 2, 3, 4, 5, all the way to n. And all this is multiplication. And from that, we were able to raise one number to another power. All this is counting, and all this is multiplication. So to take a complex function like e and raise it to a power requires exponentiation, which is raising something to a power, and being able to take the factorial of a number. But those in of themselves are nothing more but counting and multiplying. Okay? So what is multiplying? Well, we could write a function. We might do it. I don't know. I didn't feel like I had time today. Where I could write a function for multiplying. So if you think about multiplying, multiplying is just iterated adding, right? So if I take like 3 times 5, really that's just 3 plus 3, which is 6. Bring this up here, I go 6 plus 3, which is 9. Bring this up here, go 9 plus 3, which is 12. Bring this up here, go 12 plus 3, which is 15. And all I've done is added 3 together 1, 2, 3, 4, 5 times. So we could reduce it even further and say that multiplication is just adding, right? So we could go to the extreme and say a function like this, a pretty complex function, is really nothing more than just adding numbers together. Okay? And that's all of mathematics is. Believe it or not, the most complicated math problem you've ever seen in your life is nothing more than adding numbers together. That's it. So all of mathematics is just adding numbers together, or subtracting. But subtracting is just adding a negative number. And that's actually how we do it in with computers. They figured out how, well, it's like, well, how do you subtract two numbers? Oh, well, you haven't figured out the circuitry to do that. It's like, it's simple. You just take this number and you move the bits around and then add them together. That's all you do. And it's called a ones or twos complement. So it's really super simple. We're not going to get into it, but trust me, it's simple, because if it wasn't simple, dumb transistors wouldn't be able to do it. So any function that you've ever seen, what I want you to walk away from in this exam that you're going to take, in this class that we have today, is just adding numbers together. All right? So let's write a program that allows us to take e to the x power. Okay? So let's go ahead and let's insert us a module. And I'm going to call this one sub e to the x. E to the x. All right? Well, the first thing let's do, let's just get us an x. So we're going to say x is equal to input box. I'm going to just say input the value of x for the function e raised to the x power. Okay. Didn't even have to be that long. I could have just said input x, but you know. Now I'm going to create this variable, and I'm going to call it diff is equal to 1. We kind of seen something like this last week. When, remember this diff, I wanted to check to see if it was greater than the difference. And then I'm going to say count is equal to 0. And then I'm going to say epsilon, E-P-S-I-L-O-N, is equal to 0.0000001. So I've got, basically it's to 7 decimal places. So anytime you see the word epsilon in computer science and in mathematics, what this usually means is just a really small number. How small? Small enough. Okay? So don't get confused, because epsilon's like a little Greek letter. It stands for like the 5th letter of the Greek alphabet. So we're just trying to make it small. Okay? Why did I pick 0.000001? Because I feel that's a pretty small number. And then I'm going to say E2x is equal to 1. And this is really just a placeholder that I'll explain in just a moment. Now I'm going to say do while diff greater than E-P-S-I-L-O-N. And then I'm going to come down here and type in loop like this. So this is giving a little bit of an indication of where we're going with this. We're going to have this loop. So instead of doing a for next, for I equal 1 to n, and us trying to guess what n should be, we're going to kind of let this float, and we're going to do this loop while the difference between our functions that we're calculating is greater than epsilon. So just like we calculated pi last week, we're doing the same sort of thing. And I'm going to say count is equal to count plus 1. Okay. Now I have to go back here and I have to look at this function here. And I'm going to say I want to plug in this equation here. So this kind of looks complicated. Let me see if I have this pasted. Yeah, I've got it pasted. So you look at this, you're like, look, I haven't had any advanced math yet, or maybe you're not even finished with, Tech Math 1 or 2. So I don't really know a whole lot about what these mean. Well, I just explained to you what this means, raising something to a power. I explained what this means. And so this big, called sigma, anytime you see a sigma, all sigma means is summation. You just add things up. But what I really want you to see is anytime that you see a sigma that has something like, n equals 0 to, say, 8, what this usually translates into is a statement that says something like this. For I equals 1 to 8, next I. And I'm sorry, this actually would be 0. And then you add here somewhere. You have a function. That's all a sigma is in computer science. You're just looping. You're saying n equals 0, figure out the function, add it to, then what n equals 1, figure out the function, add it to, then what n equals 2. And you can pretty easily see this here. If I plug in a 0 here, well, 0 factorial by definition is equal to, turns out it's 1. So then x to the n, so x raised to the 0 is equal to what? What's anything raised to 0? 1. 1. So what you're left with here is 1 over 1. So this 1 over 1 is where this guy comes from. Well, then let's go the next one. Let's go n is equal to 1. So x to the 1 is equal to x divided by 1 factorial. That's just equal to x, which is where this guy comes from. Then we have x squared over 2 factorial. Oh, well, that's this guy. Then we have x cubed over 3 factorial. Oh, that's this guy. And you just add them up. Well, how long do you do this? Well, in theory, you go all the way to infinity. But infinity is a pretty big number, and we don't have that much time. So what we're going to do is say, well, let's do it till this number converges on to 7 decimal places. Okay? So what I'm going to do then is I'm going to write a little function. I'm going to say e2x2 is equal to e2x. So what is this e2x2? Okay, this e2x2 is really just a placeholder that I've created. So I need to get the value. It has to do with initialization purposes, that I have to be able to have a placeholder just for a moment. So we know that e to the e2x is equal to 1. So all I'm saying is e2x2 is also equal to 1, just right out of the gate. And then I'm going to let it hold the place, just like a moment ago when I said, calculate the function, add it to what you'd already calculated, calculate a new term of the function, say x to the fourth over 4 factorial, and then add it to what you've already calculated. So imagine this e2x2 is just kind of holding place. It's kind of like counting change. When you count change, you put it in someone's hand. All right, here's 25, here's a dime, here's a nickel, whatever it is. It's holding the place to add the new term to. That's all it's doing. Okay, and we're going to step through this. So if you're a little confused, don't get too upset. And then I'm going to say e2x is going to equal, and this is the only hard part of the function. It's just going to equal e2x, which is what I had, plus x raised to count. Okay, but that's not too bad, because we can see, and you have to put spaces in here for some reason, you can see that this counting is just starts out at 0, then it goes to 1, to 2, to 3, to 4. So this x raised to the count, all this is just this guy right here just getting iterated out. That's all it is. Okay, and then we're going to divide that out by application dot worksheet function dot fact count. All right, now this looks a little complicated, but this is just language. It's just like coming across a big word in the English language. They could have written something like just fact. And so you and I just wrote a program to do this. But there's a built-in program into Excel that you access, because Excel is actually pretty powerful. You can access all of its functions. Anything it'll do, you can actually access. We just accessed the factorial function. So all of this is just syntax. It's just what's required. Get over it. I can't help it. This is what we're really using. We're using factorial. Now, we could actually have written our own subroutine. And I almost had you guys do that. And I thought, nah, I don't want to do that to you. But instead of you being able to use the Excel function, I could have just written our own subroutine, and you've actually already covered this, or maybe you cover it this week, I forget, in the tutorials, where you call your own function. So we could have actually written our own function called fact, and when we put a number in, it calculates the factorial for us. But I said, I'm okay with using built-in functions. That's okay. And then I'm going to say diff is equal to ABS, which is just the absolute value, the positive value of E2 x2 minus E2x. Okay? And then I'm going to come down here and say MSG, BOX, message box. I'm going to make it say something meaningful. I'm going to do quote, E caret, quote, and X, and this is going to be E2X and after. And the only reason why I'm doing this is just to give us a little more information when we run it. but I could be lazy and just say, give me the answer. So just have like message box e to the x, and I would be done. So this is really just icing on the cake. Okay. So I want you to realize that we didn't do any coding here. All this is just giving us information. So all it's going to do is just say e to the x, which is what I'm looking for, is equal to whatever the value is after ever how many number of iterations. All right? And we're done. So let's run it and see what happens. So let's pick a number. Input the value of x with the function e to the x. So let's pick 3. And what this says is something's wrong. E cubed is equal to 1 after. Okay, so I've got a problem here. Yep, that'll do it every time. There you go. Let's try it now. Oops. There we go. So e cubed is equal to 20.085 after 18 iterations. So let's see what e cubed is. So if I say, see, 20.855. So what this told me is the reason why I entered all that is I wanted it to give us more information than just like 20.85. I wanted it to kind of tell a story that e cubed is equal to the right number to the 7th decimal place, and it took 18 iterations. So it took 18 terms for me to calculate that. So, you know, the good thing about this one is I can plug in now. No, I don't know if this will work. Let me try. See what happens if I do like 2.5. E to the 2.5. Yeah, it works. Yeah. So, my calculator. So if I take 2.5, yeah, so I got 12.18. And the reason why it works is because of, if you look at the actual equation itself, we can actually plug in values of x. I mean, this can be a decimal. That doesn't matter. And then these are always being raised to some integer power or some factorial power. Okay, so that's why you can plug in this particular case, a decimal. All right, is that pretty clear? I mean, actually, maybe it's not clear. So let's go through and take a look at it. Let's step into this. All right, so I'm going to plug in a value, say, of 3. Okay. All right, so now I'm going to step into it. So diff is equal to 1, count's equal to 0, epsilon's equal to a small number, e to the x is equal to 1. So do while diff greater than epsilon. So diff is 1, epsilon is real small. So the reason why I put this diff in is I can make diff anything starting out. But to start, diff has to be greater than epsilon, because otherwise it just falls out immediately, right? So I just put diff is equal to 1. I literally could come in here and put diff is equal to 5 times epsilon. And whatever epsilon is, diff's going to be greater than 5 or 5 times greater. So it's always going to be greater. So then I just say count is equal to count plus 1. So now count's equal to 1. E to the x is empty. But now e to the x, e to x2 is equal to e to x, which is equal to 1. Which I'm kind of cheating because I have a little intuition about programming. Really what it is just this guy. That's why I said it is equal to 1. It's like, instead of doing e to the 0 and the factorial 0, I'm just going to cheat out of the gate and say, let's just start out with it being 1. I know it's 1 because that's what the formula tells me. So that's what I'm really doing there. And there's nothing wrong with that. So then e to the x is equal to, it's going to be equal now to 1 plus e to the x e to x is equal to, this is, let's see, how does this work? So this is, count is 1, so x is equal to, it says, what does it say, 3 here? Oh, because that's the value I plugged into. So it's 3 to the 1 divided by factorial 1, which is 3. So 1 plus 3 is 4. So that's why this is equal to 4. And then my diff now is what? It's equal to 3, because the difference in this e to the x, which was 1, minus, now it's 4, the difference of that is 3, and I take the positive value of it, the absolute value, because like I said, I don't care if I'm above or below, I just want to know how close I'm getting. And then I loop around. So diff is still greater than, 3 is greater than the small number, and I just keep looping through, and this is 8.5, okay? So diff is now equal to 4.5. So 4.5, still greater than this small number, loop around. And I keep doing this, so at this point, this is starting to get a little smaller. And it's starting to get a little smaller. And it's starting to. So at this point, I'm already at 10 iterations, and diff is now down to 2 decimal places. Okay? And so this just keeps on doing this while diff is greater than epsilon. So now this diff is, it's, 2.5 times 10 to the negative 4th. I'm at 14 iterations. And it will do this until it's getting there. I'm at 17, so we know it's 18, so one more, and there you go. All right? Everyone understand that? Is there anything that anyone doesn't understand? Come on, Brandon, you always say something.
Oh no, I get it. Yeah.
No, I mean, I know you do, but you always say something in class, so. Okay, so it's actually pretty easy, right? Now, you're probably sitting there saying, well, yeah, that's easy, but where did this stuff come from? Well, some pretty intelligent people came up with this. But it's actually not as bad as what you think. And I almost would show a video in here, but what I would rather you guys do is to watch it on your own time, because I want to cover. But, click on this Taylor series video and watch it. It's only about 20 minutes long, and there's probably going to be a lot of things you don't understand in it, but that's okay. I want you to watch it because it's going to give you some insights into where these equations actually come from. That it's not actually just like someone sitting around and like, well, let me try this raised to this power and take the factorial of this. It's actually a pretty straightforward process that they use to derive these functions. Okay? So we're going to do one more. And so I'm going to give you a heads up on what your exam is going to be. Your exam is going to be, you're going to be randomly assigned either a sine, a cosine. I didn't give a tangent. The reason why I didn't give a tangent is because you have to calculate what's called Bernoulli numbers. But actually there's an easier way around it. If you remember your trigonomic identities, you can calculate the sine of theta. The tangent of theta, I think it's the sine of theta divided by the cosine of theta. So if you really wanted to calculate the tangent, you just calculate the sine first using this formula, the cosine using this formula, and then divide the two numbers out. And then to calculate the arc sine and the arc cosine and the arc tangent, you may have to calculate one of those, but those are basically just inverse functions. So if the sine of 45 is like 1/2, then the arc sine of 1/2 is 45. Now it's in radians, so you will have to do some conversions from degrees to radians. Remember how you, pi over 180? I talked about that earlier in the class. And then you may get one of these hyperbolic functions, either a hyperbolic sine or hyperbolic cosine, which they have to do with hyperbolas instead of circles. But that's okay, because I don't really care if you know what these mean. There are functions within Excel that calculate them. So what I want you to do is you to go in, write the little program to calculate it, and then do a comparison between, so if you use your calculator and you say, okay, I'm going to calculate 0.78, I'm going to calculate the sine of that, and you get this number, okay, use that to check it. Use Excel to check. I'm okay with that. I just want you to go in and understand this algorithmic process. Okay, so we're going to do one more. We're going to take the log, the natural log of a number. So for instance, here's a good one. If I take the natural log of 2.7182818, and I take the natural log of that, watch what happens. I basically get 1, because the natural log is basically asking, you know, what power do you have to take e to? Okay, so if I take, like, say, the natural log of 20, what this tells me is I essentially have to take e and cube it, and I get 20. So that's what this natural log, it's figuring out the reverse of this. So for some reasons that are in that video, these are only valid over the range, basically, of 1 to -1. Okay, it's called the range of convergence. So this formula doesn't work on the infinitude of numbers. Okay, but we can use a little trick to make it work, and this is what mathematics is all about. It's all about using tricks. So if I can only take, say, the log of x, but x essentially has to be less than, say, 1, so say I'm going to say 0, okay. Actually, this is -1, I should say. Then how can I let x be like, 208.36? Because x is outside of this range. Well, there's a little trick that you probably know. If you don't know, you're going to learn it. Is the natural log of 1 over x is equal to negative natural log of x. So it turns out, I can let this number be as big as I want, because if I take the natural log of 1 over 208, that's just going to be equal to negative the natural log of 208. Okay, so let's try it. Let's take the 208 and take the natural log of that, and I get about 5.33. So we'll take the negative of that. All right. So now I'm going to take 1 divided by 208, and I'm going to take the natural log of that. So look what I get. I get negative 5.33. Does everyone see that? And these are just the laws of logarithms. Okay? So essentially what you're really doing is you're just saying the natural log of x to the -1. Remember, when you take the log, what you do is you pull this guy out and you get -1 times the natural log of x. Is really how that's working. Okay? If you don't know it, forgotten it, don't sweat it, because you can use your function on your calculator. The purpose of this class isn't to explain logs and natural logs and Taylor series and all that sort of thing. We know what sines and cosines and tangents do, but how do you get those numbers? And that's what we're going to learn. Okay, so let's do one more of these, and so let's just do a little cheating. Let's just take Control-C, and so just highlight it and hit Control-C or File Copy. Do a Insert Module, Control-V, and I'm going to call this guy lnx, like this. And I'm going to come here and say input the value of x for the function natural log x. Okay. And then I'm going to do a little trick here, a little trickery. I'm going to say x is equal to 1 minus 1 divided by x. I'm going to explain where that comes from here in just a moment. So I'm going to take x and I'm going to transform it. And I'm going to leave this the same, leave this the same, leave this the same. I'm going to do this. X2x equals 0. Diff, that's the same. Okay. So now all I'm going to do is change this to count. And then I'm just going to come down here and say ln, and then instead of okay, one other little thing. Let me type up here. We'll type in value equals x. And that is really of no consequence. I'll explain that. Okay. And that's it. Okay. So the only thing I really changed, if you'll notice, is just this formula here. And why did I change the formula? Well, the reason why I changed the formula is because the formula changed. So the formula for this notice instead of a factorial here, I just had n. So it's actually simpler. So the log is actually simpler than the e to the x. So before I had a factorial here, now I just have n. So that's really all I changed. All right? So that's it. And this value up here, when I have value equal x, the only reason why I had value equal x is because I transformed my value of x, and I need to keep track of what my original x value was so I can report it. All right. Now, why did I do this? Why did I say 1 minus 1 divided by x? It has to do with just the formula. If you look at the formula, what they say is, they don't say that the log of x, so you can write log as either log or ln. They don't say the log of x is equal to this formula. They say the log of 1 minus x is equal to the formula. Okay? And that's only valid for x is equal to between 1 and negative 1. That's another stipulation that if you look, that it clearly says they converge only for these values right here. Okay? So because of that, what I have to do then is I say, well, the log of 1 minus x, so what is x? Well, if x is a big number, remember what I'm going to do is take 1 over x. Okay? And by taking 1 over x, then I make this negative. So if I make this negative, then all of this becomes negative. I don't need that. And then what happens is a negative of a negative becomes a positive, and all of these now become positive. Okay? So that's what I did. That was the little trick that I did. But that's not so much has to do with the coding part of just the mathematical manipulation, and that's why I don't have negatives. So you notice that I have e to the 2x plus. You may look at it and say, well, wait a minute, the formula says minus. You're doing minus, you're doing plus, but it says minus. And I say, yeah, but we're doing this for larger numbers. We're looking at this for, like, if I want to take the log of like 1,000, and because of just how the mathematics work out, it's the negative of the log, which gets rid of all of these negatives and makes them all positives, but it's the log of 1 minus that small value. So that's why I had to put this function in right here. Okay? Otherwise, it'll calculate the right answer, but it'll be to the wrong problem. Because if you ask the question, if you want to know the answer to the log of, say, 0.3, and I say, oh, well, I can't tell you what the log of 0.3 is. I don't know how to do that. But I can tell you what the log of 0.7 is, okay? Because that's just how the formula works. And and I don't know why. Maybe because it turns out that it's the most simple form of writing it in this way, and mathematicians will do that. So you not only ask the question, you have to like transform the question just a little bit. But that's super simple to do. Say, well, what's the log of 0.3? It's like, well, I don't know, but I can take the log of 0.7. It's like, well, that's good enough. I'll just take the log of 0.7 and take the opposite of it, and then we're good. Okay, does that make sense? All right. So let's try it. Come up here and let's run it. So let's suppose we want to take the natural log of 30. So it says the natural log of 30 is 3.4. Well, let's try. So 30, take the natural log, and there you go. Now it took a little bit longer. It took 307 iterations to get there. I'll give you some insight as to why it took longer for it to get there. The reason why it took longer for it to get there has to do with these values here. They just grow linearly, whereas when we looked at e to the x, these values down here grow factorially. So it just takes a few more iterations because your numbers aren't growing as fast when you're dealing with the log versus the inverse log or natural log. But it also has to do with if you just graph these two, one of them, e to the x looks like this. The natural log of x looks like this. So this one grows really fast. This one grows not so fast. So it just takes a little longer. That's kind of the intuitive reason. But it doesn't matter. Okay, 300 iterations compared to 18. The computers can do a billion a second, so it's trivial. Okay? All right, so like I said, your exam is you will randomly be given one of these functions, and you have to write a program that does a couple things. So I'm going to I'll click on this and see which one it randomly assigned me. So I got assigned the hyperbolic cosine. So there's two things that I want you to do. I want you to write two programs. The first program is just what we've been doing. So call it COSH Taylor in sub and put your code here. So what I expect is to paste your code something like this, COSH Taylor, then I'll say code, and then I'll say end sub. So put your code in here, and then for the second part of your code, put it in here. So what I want to be able to do is to open up your assignment, highlight this. Well, it'll let me do it, but highlight this. I hit Control C, go to Excel, hit Control V, and then hit Run, and your code works. For the second code, what I want you to do is not just to do it for one number. I want you to do it like we did when we calculated pi. I want you to like do a for and x do while loop that say list all the angles from 1 to 89. Why not 0 and 90? Well, because sometimes you get like undefined at 0 and 90. So let's just do 1 to 89. List 1 to 89. The actual value of the hyperbolic cosine, which is just COSH parentheses, that cell value, pull it down in Excel, and then the value you calculate for each one of these in column C, and then the number of iterations required for six digits of precision. So let me show you how you would do this like A and B. I'm going to show you how to do this. So you type in 1, 2, 3. You're going to do a for and x loop that'll list these, but this is basically what it'll do. It'll count from 1 to 89, just like this. And then you'll come up here and you'll say equal COSH calculates the value of that. You can double click, brings them all down, okay? These are actually some pretty big numbers. I didn't realize it was going to do that. Yeah, but it doesn't matter. If it bombs out, I don't care. I'll still give you credit. It doesn't matter. And then whatever your algorithm calculates these values to be will go here, and then the number of iterations required. So some of these numbers might actually get huge. I don't know. Try it and see what happens. I didn't actually try it for these hyperbolic functions. Okay? So that's all I want you to do for your exam. But I want to be able to take and just copy and paste it and watch it run. And I'm not looking for an Excel file or an explanation of you do this or that. I should be able to Control C, Control V, hit F5, F5, and it just run. Okay? So you should be given, at this point, you should have enough information to do this. The log and natural log and exponential function. I kind of showed you how to do the for, next, do while loops with the epsilon. Then you'll just plug into these formulas right here and, look back what we did with calculating pi and how you actually put those values in cells. And, you should be able to do this in a pretty reasonable amount of time. And so then, what I hope you get from this is an appreciation for what sine, cosine, and tangent, how they're calculated. Because all these years you just hit a button on your calculator and you maybe you thought about it, and then you're like, I don't know, somebody figured it out, I don't care. But now you're going to know how these work every time you hit the button on your calculator and use a function on the computer. Okay, and don't forget the participation assignment, that's also due. So these are due next Tuesday right before class. So you've got about a week to do this. Okay. If you paid attention, you have some intuitive feel. Literally, these are problems that you might be able to finish in. I could probably do each one of these problems in 5 minutes. Now, I'm not bragging on my abilities because, okay, I've been programming a whole lot longer. But I'm saying literally it could be that simple. That these are not really hard problems to do, but I do think you'll get something out of actually going through. And the good thing about it is you actually get to see if it works. So you get to plug it in, and if it gives you an error message or if it gives you the wrong answer, you get to go in and say, oh, there's something that I did wrong. Okay? Any questions? Well, if there's no questions, then I guess we're done for today, and I'll see you guys next week.